Okay, this is your notes for section 3.10, and in this section we're going to talk about differentials. So let's get right to it. The Leibniz notation dy dx, which we've used a lot, has been used to mean the derivative of y with respect to x. Okay, now up to this point we've treated dy dx as a single symbol, and we've not given separate meanings to the symbols dy and dx. In this section, we're gonna describe what we mean by dy and dx. Okay, we'll also talk about some other things here. Definition. Okay, let y equal f of x be a differentiable function on an open interval containing x. Okay, so I can take a derivative anywhere on this interval. Delta x, and this is a capital delta in Greek. We've seen a little delta back when we were doing delta epsilon proofs. Remember, here's a small delta in Greek, here's a capital delta in Greek. Okay, so delta x is an arbitrary increment of x. The value of delta x can be positive or negative. Dx is called the differential of x. Dx and delta x mean the same thing. Okay, it's some increment away from x. Delta y is the change in y as x changes from x to x plus delta x. So delta y would be f of x plus delta x minus f of x. Dy is called the differential of y. Dy is defined by dy equals f prime of x dx. Okay? Now, in this section, we're giving separate meanings to dy and dx. Dy dx is notation that we use to represent f prime of x, right? So if we're describing these symbols individually, I am basically multiplying both sides by dx here to get dy. All right, now let's take a look at a picture. The geometric meaning of differentials is shown in this picture. Suppose that we have a point P on the graph of some curve, and point P has coordinates x, f of x. And point R is also on this curve. Point R is located some increment away from point P of delta x units. Okay, now remember, delta x and dx mean the same thing. The slope of the tangent line, PQ, is the derivative, f prime of x. The directed distance from S to Q, that is the rise-fall distance, is what we're calling dy. Okay, now notice that dx and delta x are the same thing. You're talking about some increment away from x. But dy and delta y are not the same thing. Okay, dy is the rise-fall distance on the tangent line. Delta y is the rise-fall distance on the curve. But dy and delta y are going to be very close to each other if dx is very small. You know, if I go some small increment away from x, the gap here is not going to be much. Of course, for a large increment away, you have a big gap. So for what we're doing here, you know, to be reasonable, you would assume that dx is some small increment away from x. Okay, now here's a formula that we're going to be using in some of the problems later. F of x plus delta x would be this distance here, that point R is from the x-axis, and that distance is going to be about the same as f of x plus dy. That's where point Q would be located. All right, so in other words, the distance from R to the x-axis and the distance from q to the x-axis are going to be roughly the same number as long as dx is a very small number, okay, close to 0. So dy represents the amount that the tangent line rises or falls. Okay, that's the rise-fall distance on the tangent line. Whereas delta y represents the amount that the curve rises or falls by some amount of dx units. Okay, so that's the rise-fall distance on the curve is delta y. From the graph, it would seem reasonable to assume that for small values of dx, the y values on the tangent line can be used to estimate the function values on a curve. Okay, that's what we're going to be doing in this section. We're going to be estimating values from a derivative. All right, and here's this formula repeated again. Now there's a note below that. Derivatives and differentials are not the same. When you write dy dx, you're using the symbol for a derivative, and we've been using that all over the place, right? That's the Leibniz notation for representing the derivative of y with respect to x. When you write dy, you're denoting a differential. Okay, you are just simply talking about the rise-fall distance on the tangent line, not the left-right distance. Okay, of course, with a line, in slope, it's rise over run, right? Do not be sloppy and write dy when you mean to label a derivative. That will lead to confusion in this section and also later on. Differentials are going to come up again. Just kind of the notation is going to come up again for something later down the road. And so we got to make sure that we don't get this confused with derivatives. Now we're using derivatives to talk about differentials, but they're two different things though. Let's get some practice at finding differentials. Now, when we find the differential dy, we're using this formula here. We need to find f prime of x dx. Okay, so dy in problem 1 would be f prime of x dx. Now, f prime of x would be a chain rule. So you're going to bring down the power of 1/2, reduce the power by 1, and then take the derivative of the inside, which is x squared plus 3x. The derivative of that would be 2x plus 3. And then I want to tack on a dx. If I simplify, okay, I'm going to have 2x plus 3 divided by 2 times the square root of x squared plus 3x if I use radical form dx. All right, make sure that you have the dx there. If you don't, then you're getting confused with a derivative, right? I'm not asking you to find dy dx, I just want to find dy. So you need to make sure that the dx is on the other side there. How about problem 2? We want to find the differential dy. Okay. Well, I need to find the derivative and then just tack on a dt since the variable is t here for this problem. The derivative of the ln of an expression is 1 over the expression times the derivative of the expression. So I'm going to say 1 over t to the 4th minus 3t squared plus 11 times the derivative of that. The derivative of t to the 4th is 4t cubed minus the derivative of 3t squared, that's 6t, minus 6t. Derivative of constant is always 0, and then just make sure that you've got the dt on the end. Really, there's, the only new thing here, as far as the notational stuff, is just make sure that you got a dx or dt or, whatever on the other side. Problem 3, okay, y is equal to 2x minus cotangent squared x. The differential dy, okay, when I find the derivative here and then tack on a dx, I'm going to have the derivative would be 2 minus, here's going to be a chain rule, so I want to bring down the power, reduce the power by 1, and let's see here, so of course I'm using the chain rule, right, so bring down the power, I'm leaving cotangent x alone, but then I got to multiply by the derivative of cotangent x, which is negative cosecant squared x. Make sure there's a dx afterwards. 2 2 is in common to these two terms. You can factor that out. Okay. So I brought that out front here. You're subtracting negative. That means you're adding. Okay. Problem 4. Y equal e to the negative u times cosine u. Let's find the differential dy. Okay, so this would be a product rule, right, to begin. The first is e to the u times the derivative of the second. That'd be derivative of cosine u is negative sine u, and then plus the second is cosine u times the derivative of the first. The derivative of e to a power is e to the power times the derivative of the power. So it's going to be e to the negative u times the derivative of negative u is negative 1. Make sure that you got du then at the end. And of course, make sure that you got the correct variable that you're using. You know, like I'll see students write dx when it should be du or dt or something like that. Okay. Negative e to the negative u is in common to these two groups. So I'm going to go ahead and factor that out of the whole thing. And the leftover then from the first term would be sine u. The leftover from the second one would be cosine u. And of course, don't forget to also include the du part at the end there. Okay, so these are just some computational problems, getting some practice, where finding differentials. Okay. Why don't we'll stop the video here, and I'll finish up the section in the next video.